Alright, today, my good people, I want to give you a thorough introduction, because I realize that most of us don't still understand the things I've been posting, those videos and the notes. It's like they are not properly understood. So I want to go to the elementary ways of how to program microcontrollers, and how to simulate. So today what we are going to do is we are going to simulate a program that simply blinks or blinks LEDs. All right, we have LEDs that are connected. Uh, then we blink them. That is, we turn them on and off sequentially, one after the other. So to start with, we open our Proteus to do the design. Okay, we have to design our circuit first. We go to Proteus and then we go and pick our components that we are going to need. Of course, we know we are going to need PIC16. That's now PIC16F what 877. Right, A. We choose the A. I know we are going to need a resistor. Okay, we pick that. We are going to need capacitors. I'm going to explain this later on. We are going to need a crystal oscillator. Okay, we pick that, and we are going to need an LED. LEDs, now we have a lot. Down here we check the generic one. Okay, we use which one do we use? Let us use red. Okay, use that. Apart from that, what else do we need? I think that is it. Right, so after we have finished picking what we need, we close that. We come and place our components in the design area. You can see the design area, so your components must be within this blue square line. All right, you place your microcontroller there, and after placing your microcontroller, the next thing you want to do is now to place your components, the way they will interact, or the way they will work with the microcontroller. So we always start off by connecting our oscillator. Okay, we click our oscillator. Like now we have it this way. We can decide to turn it around this way, okay, or we can leave it that way. So let us leave it this way. We put it here, but let me just zoom in a bit. Right, so you would see that in your microcontroller here you have oscillator 1, oscillator 2, or clock in, clock out. Okay, what oscillator does, it actually acts as a means of updating the microcontroller, refreshing the microcontroller, so that after every set period of time, it updates the microcontroller, so that the microcontroller will be acting, or actually reading what is what the program currently tells it to do. Right, so what we are going to do, let us drag it down a bit, so that we will have the our oscillator will be connected between these two pins, that is pin 14 and pin 13 of our microcontroller. And then we will have capacitors that will be connected also to the oscillator there, and then to the ground. Okay, like so. Let's just pull this one down a bit, so that They are nicely spaced. Then you will need to pick a ground. So to get your ground, you go to terminals. This way you get your power and the ground and all that. So for now we need ground. We pick our ground, we place it there like so. So we are done with the oscillator, though we are yet to do some settings, but we are coming back to that. So the next thing we want to do now, let us go back to our devices, and then we are going now to place our LEDs. All right, we will have let us say we use port B as our digital output. So this is where we are going to connect our LEDs, and therefore we are going to pick an LED. You can decide to have them pointing down, all of them, or this way, but I prefer them pointing it down, so I will have them like so, 8 of them. I hope they will fit. Cancel that. Like so. How many are they now? 5, 6, 7, 8. Okay, then I will have this one there, that one I'll connect it there, this one here. Okay, sorry, this one should come here, and this one come to this guy, this one to this one, that one to this guy, and that to that one. Okay, sorry. Okay, so now with the resistors, because these are LEDs which don't take a lot of current and a lot of voltage, so we need to limit the current that flows through them, and we do that by using a resistor. So you can decide to have 8 resistors, okay, each one of these ones having its own resistor, but for this for the sake of this lesson, we are going to use only a single resistor, so that all of them will be connected to this single resistor, like so. Okay, after all, only one LED will be on at a time, so we are not worried about the total current, because we'll have only a single current flowing at a time through the resistor. That's why we can conveniently use a single resistor. Okay, so we can decide to connect this, because this has to go to ground now. Okay, and also take note of the orientation of my LEDs. So I connect them such that the cathode points down, which is going to be my ground, so that is forward biased. Okay, just take note of that. So I can decide to connect now this one to this ground here, but I would prefer to have another ground terminal there. It's the same. So in a circuit like this, whether you have 100 grounds, they are treated as a single connection, so it doesn't matter. Alright, so I can have that. So then I can now start setting up my these things. Alright, that is now to say what should be the value of my resistor. If you make it too big, then you will not even see that the LEDs are on, because it will limit current so much that only a little current will go through that. So you can make it 1K, 1 kilo ohm is fine, or I can, if you want it to be really bright, I can even make it 330 R. Okay, 330 ohms, so that we indicate it by R. If you put R, then it means ohms. If you put K, then it's kilo ohms. Okay, how much of this, how much frequency should my oscillator be? We know that according to our data sheet, PIC16F877 uses 80 gigahertz. So I must set this one to 8 gigahertz. By default it's 1 megahertz, so I change that one to megahertz. You can change also the part reference. This one you can change, even for this one, even the value you can change it to whatever you want it, but for now let us leave it that like so. Generally our capacitors we use 22 picofarads, so I come there and I change this to 22 picofarads. Make sure that the P is small and that's lowercase and the F is uppercase. 22 pico. Alright, then I make this one also 22 pico. One thing about these two capacitors that they must all be for the same value. So if you use any other value apart from 22 pico, so make sure that both of them have that same value. So I think by now we are ready to do programming. So basically what we want to do is to turn on this LEDs sequentially in 10. So to say, for example, we start with this one goes on, after some time it goes off, then this one goes on, after some times it goes off, and this one comes on until we reach this one. After that we come back and start over, and then we keep doing that one for a number of times. Okay, so now to do that, so this by the way, this is called a simulator. Proteus is a simulation software, so we are basically simulating what we could have done physically if we were to have physical LEDs, connect them either in a breadboard or a PCB, printed circuit board, and we have a circuit like this, and we want the circuit to do exactly what I just described, turning on these LEDs one after the other. So to do that, we will have to create the circuit itself, hardware, and then we will have to write a program separately, and then that program must now be written or kind of uploaded onto the chip, on the chip, on the microcontroller itself, so that microcontroller using that software can now control the sequence of turning these LEDs. Okay, let us quickly go and do the programming. Alright, to do that we of course have to come to our MikroC Pro for PIC. Come to that, open it, wait for it to open, and while it's opening, let me just make mention of the fact that what we are going to use here is what we learned to be the for loop. Okay, not for loop but while loop. Let us use a while loop. Of course we could use a for loop and all that, but for now we are going to implement a while loop, what we have learned in our programming principles 1 first semester. So after this has opened, we create a new project. It will bring up this dialog box here, that wizard. We just go to next, and then here is where we have to do a lot of settings or changes. So number 1, we change the name of our project. Let us call it LED for now because we are dealing with LEDs. And then the folder, the project folder, that's the location. You can go to browse and then choose where you want it. So for me, I have created a folder called LED blink. I just click on that, say okay. Then here, if you are using this for the first time, you will have to indicate the microcontroller you want to work with, so otherwise this software will remember your previous microcontroller that you have used. Since I have used this microcontroller, it's already there, but otherwise you will have to set the microcontroller you are using. You have to select it from that list, and also here you must also indicate the frequency. Remember the frequency that we have set here for our oscillator. Even in the software also you have to indicate them the oscillator frequency. Alright, after I've set that one, 8 megahertz, we go to next. Here you do nothing, you just click on finish. After that, then a program, an editing area will open up with already a template of a function there. Okay, in Java we call them methods, but in C we call them functions. This is our main function, void main, which starts from there and ends here. So here, this is where you do your programming between these two brackets, the first parenthesis or bracelets and the last one. Between there is where you put your program. So we start off by kind of telling the compiler how we want to use our microcontroller. So like we said, you have a microcontroller like this one. It has a number of ports, about 5 ports I think, for this one, because it has A up to E. So but what we have done in our design, we have used port B, the bits of port B. Those are the bits we have used. Okay, so we are going to tell our, and like in this case we are just using this port B as our output, because we are actually writing something on this port, so that whatever we write here should appear or should kind of control. It's actually an output, so we are using this port B as an output. All right, so we are going to tell now the compiler that we are using port B as an output. This one we cancel. Right, so how do we do that? Like we explained in the previous lesson. So we do that by telling or by using a trace register, telling the compiler to set trace register, trace B to be an input. And how do we make it, I mean an output? How do we make it output? If is when we put a 0 there. If we put a 0, it's an output. If we put 1, it's an input. Right, so but we have to use, generally we use hexadecimal, okay, number. So you can use decimal number, you can use binary numbers, you can use octal, but we will be dealing with generally most of the times we are going to be using that is now hexadecimal. So hexadecimal always starts with 0x, okay, small x, and then the number. So I put 0 zeros there to indicate that all the 8 bits should be zeros. Okay, if you make it 0f, then you have the first 4 bits outputs. You are putting zeros on the first 4, and then the last 4 they will be input. The F is 1111. Okay, so but we want all of them, 8 of them, to be outputs. Okay, so we say trace B is equal to zeros. All of them, we are actually writing zeros on all of those. Okay, so and since that's the only port we are dealing with, so we are done with setting our this thing the direction of our bits. So we go to the port itself, that is the initialization. We go to initialize to say at the beginning what should be at our ports, what should be the status of our LEDs that are connected to those ports. So we say port A, not A man, B, port B is equal to 0. It's a common practice that whenever you are starting, you want to make sure that all your ports are zeros, except in some isolated cases where you want to start with some different values, but otherwise we want to clear all the ports first before you start using them. So we clear our port bits first, and then we now start telling the compiler what to do with these bits. So let us look at our design and decide which order we want it to be turning this LEDs on. Do we want to start with this one, the left, the far left one, going in this direction, or do we want to start from right going to the left? If for now, let us say we want to start from left going to the right, and that way, right? Okay, if we are going to start now from the left, which means we are going to start with this bit here, okay, bit 7, which is RB7. RB7 is what we are going to be dealing with. Is the one that we're going to start with. So what we are going to do now is we are going to tell our compiler or the program to turn on that LED. So we say port capital sorry, we say port B dot there are now different fashions. You can say F7, ne? That is for F for that one. Otherwise we can also say RB7, ne? RB7 is equal to 1. Okay, so you see now that all your things are underlined in red, telling you that something is wrong. That is just because you did not run your program. Okay, so but at this point I want to save so that I get rid of these reds, so that I will know when I'm doing something wrong or so. So number one, you have to save and then to build. But what I want you to understand is that eventually we are going to get the file that we create. Okay, the file that we are creating, we are going to upload that file in our this thing, in our Proteus here. Okay, that's what we are going to upload. But which file are we going to upload? Let us first save. Of course we save it in that place, save it there. So once you save it, you see that that file is there, but this is not the file we are going to need. We are going to need an hex file. Okay, if you click on this one, you see that it's asking for a program file, and this program file must be hex dot hex, and the one we have here now, let me just close this, the one we have here is .c. So that's the C file. That's not what we want. That's the one we are using to do our programming, but we will need the .hex. But the moment you build, if you build, it says compile and all that, and until it finish successfully, then it should create now many files here, and one of those files must be a .hex. Okay, that one, that's the one that we are going to put in our microcontroller here. Let us continue with our programming. Okay, so we tell our compiler to switch on a bit RB7, make it 1. By making it 1, you know, now this one here is in decimal. That's why we are not using 0x. So if we use 0x, then that controls the whole what is it now, the whole port, the whole port bits. So with hex, you cannot just control a single bit, you have to control all the bits. So like this, it affects all the 8 bits, né? But with decimal, you can control a singular bit. So we do that, just we use now decimal to control a singular bit. After that, we want to tell the compiler how long should that bit be on, né? Remember at the beginning all of them were 00, so all of them were off. Then at this point all of them are the other 7 are still off. Only bit 7 or bit 8 actually, RB7 is on. Alright, so the rest are still off. So we want now to tell the compiler how long should this RB7 be on. Okay, so we control that by calling a delay. We say delay underscore ms, standing for milliseconds. Then we open a bracket, close the bracket, and end with semicolon, and inside the bracket we indicate the duration in milliseconds. If we say 1000, okay, if we put 1000 there, it means 1000 milliseconds, and 1000 milliseconds is equal to 1 second. So which means this this bit is going to be on, or this LED, the LED connect to this bit is going to be on for only 1 second. after which we must turn it off, ne? So I come and copy that, put it here, but now at this time it must be off. Turn it off, turn it off, and then turn another one on. Now the one that is going to be on is going to be RB6, because we are coming from 7 going up to 0, ne? After that we wait for 1 second, and then we turn this one off. RB6, which was on, we turn it off, ne? Turn it off. Okay, turn it off, and at the same time turn on RB5, ne? Okay, turn off. My indentation is not working fine. It should be this. Then all right. Okay, RB6 is now off, RB5 is on. Then we must delay for 1 second again. Okay, let me just copy this part so that we are a bit fast. All right, so after that we turn off RB5, we turn it off, and then RB4 we turn it on. Okay, after that we wait again for 1 second, then we turn off RB4 and turn on RB3. After that we wait for 1 second, then turn off that RB3 which was on and turn on RB2. After that we wait for 1 second and then turn off RB2 and turn on RB1. After that wait for what now? Wait for 1 second, turn off RB1, and turn on RB0, which is the last one. So like that we have gone through all of them and all that, and then now let us wait for another one second, and then turn off that RB0. Okay, turn off RB0 so that it doesn't remain on now after we are done with everything. Okay, right, so let us quickly save that, save all, then run it, that is build. Then we come and upload now. Of course we must upload our hexa file, that hex file. We go to where we saved it. All right, pp2 examples led, and then you see the hex, the .hex file. Okay, we put it in there and change it there, frequency also to 8 megahertz. Then we click on that and then we run it here. Run. Let us see. This is the moment of truth. Cross our fingers. Okay, okay, okay. All right, all right, all right. Now you can now see that it cycles through once. So we have successfully managed to turn our LEDs one after the other, so with delays of 1 second in between. But the only thing we have now, the problem we have now, is that it only goes through that cycle once. After it turns all of them on and off, then it stops. So we want a situation where we are going to use, like we said, a while loop. So that is going to repeat that thing okay, that process, maybe let us say 3 times. Okay, so to do that now, after we have started, we say while, okay, while, open and close bracket, we put what now? Before we do that, we must declare our variable here. We say counter, and we initialize it to 0 at start. Okay, right, we say while counter is greater than where's greater than now? Greater than 0. 3, 2, 1. Okay, greater than 0. Then we do this. All right, we do all this, and at the end here, close this our bracket, but we must now say counter plus plus, plus plus. Actually, then if we are plus plus and our counter started at 0, then we must say while it is less than 3. We start from 0 until it reaches 3. Okay, let us build. What happened here? Is invalid expression. All right, I think I just had forgotten something here. So actually, in this microelectronic C, our variables are defined, or rather declared outside the main. Okay, so you don't declare them here, but you declare them outside here. So that's where we declare our counter. So if you put it inside the main function, then you are going to get errors like I just did. All right, so you declare your counter there and also initialize it to be 0 at the beginning. Then you now come and say while that counter is less than 3, you keep doing this one, and then after each cycle, you increase your counter by 1. That increment thing, counter plus plus, increases it by 1. Right, we run it again. I think here I deleted my semicolon. Okay, run it again. So after running it again, so sometimes this one will pick it up or automatically, but sometimes it doesn't, so you need to just reload that hex file again. After you have done some changes, then you run it. Let us see if it repeats it 3 times. Okay, as a second time repeating that one. Okay, third time, at the third cycle. Then after that it stops. So after the third cycle, it stops. It doesn't continue anymore because our counter has now reached 3, so it's no longer less than 3 according to this condition here, because we said it will only do this one while the value of counter is less than 3. So once it reaches 3, then it will evaluate and realize that 3 is not less than 3, so it doesn't repeat that anymore. So basically that is how you program a microcontroller in C, and we have just successfully programmed a circuit whose function is just to turn on and off the LEDs, 8 LEDs in a sequence. All right, so if you feel your LEDs are not bright enough, you could reduce the value of this resistor. Okay, otherwise if you feel they are too bright, you could increase the value of resistor. But in practice, please make sure that this resistor is not too small, because otherwise if the resistance is too small, then you send a lot of current through this, which can destroy the LED. All right, so otherwise that is that for today. Thank you very much. Stay well and God bless you.